5A, probability, basic ideas. So now we're starting into probability. A probability experiment is an experiment in which we do not know what any individual outcome will be, but we do know how a long series of repetitions will come out. Such as, if I flip a coin, I don't know whether I'm going to get heads or tails as a result on any individual toss. But I know that if I were to do that over and over again, that half the time I would come out with heads and half the time I would come out with tails. So that's a probability experiment. We know that in the long run you're going to come out with this probability of it occurring, but on an individual basis, we don't know what the result's going to be. The probability is known as the proportion of times that an event occurs in the long run. Like I said, if I flip a coin 1,000,000 times, half of those would be head, half of those would be tails. So in the long run. Sample space is the list of all possible outcomes of a probability experiment. So it's not how many possible outcomes, it's the list of all possible outcomes. Such as with this example of flipping a coin, the sample space would be heads and tails. That's the sample space. It's the list of all possible outcomes. It's not how many possible outcomes. There are two possible outcomes, heads and tails. But the list of all possible outcomes. If I were to roll a six-sided die, 1, 2, 3, 4, 5, 6. That would be my sample space, the list of all possible outcomes. An event is an outcome or a collection of outcomes from a sample space. So I may have the event of getting a heads if I flip a coin. If I roll a die, an event may be rolling a 3, or it may be rolling an odd number, 1, 3, or 5, or a number less than 6, so 1, 2, 3, 4, 5. So that would be an event. Now that we're familiar with those terms, let's look at classical or theoretical probability. As I fight the streaky board. Okay, so classical or theoretical probability. So classical or theoretical probability is simply the probability that event A occurs is equal to the number of outcomes in A over the total number of possible outcomes, or the number of outcomes in the sample space. So theoretical probability, the probability that event A occurs is equal to the number of outcomes in A or the total number of possible outcomes. So if I'm talking about flipping a coin, the theoretical probability of getting heads is there's one way to get heads on a coin out of two possible outcomes, heads or tails. So the probability of getting heads is 1/2. The probability of rolling a 3, if I'm rolling a six-sided die, there's one way that I can get a 3 out of 6 possible outcomes on that die. So 1/6. The probability of rolling a number less than 6. So if I'm rolling a die and I want the probability of rolling a number less than 6, there are 5 numbers less than 6 on that die out of 6 total values, so 5/6. So that's how you come up with your theoretical probability. And a couple things you need to realize with this is that your probability is always going to be between 0 and 1. So probabilities are always between 0 and 1. You will never have a probability that's less than 0, you'll never have a probability that's greater than 1. In fact, if you have a probability that is equal to 0, that means that the event will never occur. If you have a probability that's equal to 1, that means your event will always occur. And then any other probability, anywhere in between 0 and 1, is the likelihood. The closer your probability is to 1, the more likely that that's going to occur. The closer your probability is to 0, the less likely that it's going to occur. In fact, a probability that's very close to 0 tells us that we have an unusual or an unlikely event, or a rare event. And what is considered to be a rare event? What type of probability? Well, that really matters on what are you checking and why do you care. Some people may use 0.05, which means 5% of the time it will occur. Some people may use 0.01, meaning 1% of the time. Well, it really depends what you're dealing with. If you're just talking about flipping a coin, then the probability, who cares? If you're off, it's like if the probability that it occurs is off by 5%, nobody cares. Whereas if you're talking about, as I used to have to deal with, creating a chip that will go into an airplane and be used in thousands of places or thousands of circuits in that airplane, then I don't think that having 5 out of 100 chips failing is a good thing. To me, that's not rare. If I've got 1,000 of these chips in an airplane and 50 of them are likely to fail, that's bad. So obviously, what I would consider an unusual event in that case would have to be something that's much more rare, maybe 1 in a million chance that it's going to fail. That's what I would consider an unusual event. So this is theoretical probability, of course this is probability in general, but we talked about theoretical probability, which is just number of desired outcomes or the total number of possible outcomes, and now we know that it's between 0 and 1. But another type of probability that we deal with is experimental probability or empirical probability. Now, obviously you're familiar with the empirical rule, right? But you've heard empirical before, such as people say empirical evidence, right? That's your experimental proof. You show it by actually doing. So empirical or experimental probability is just that. You go through a number of trials, do it over and over and over again, and you count how many times does it actually occur. So empirical or experimental probability, the probability that event A occurs is equal to the number of occurrences over the number of trials. So let's say I take a die. I've got a die, and I roll this die 10 times. So rolling this die 10 times, I get, and actually let me put something first. Let's find the experimental probability that I will roll a 3. So I roll it one time, I get a 4. I roll it again, I get a 6. Again, I get another 6. Again, a 3. Again, a 2. A 6. A 5. And a 1, 2, 3, 4, 5, 6, 7. So 3 more times. A 2. A 4. And a 2. Okay, so I rolled this die 10 times. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Out of those 10 times, I got 1 3. So my experimental or empirical probability of getting a 3 is 1/10. Or if I write it as a decimal, 0.1. Well, let's look back at theoretical probability. Theoretical probability of rolling a 3 was 1 out of 6, which is 0. I'm going to put this right below just so it doesn't get in the way of the other thing. 0.16 repeating. So we see that my experimental probability, 0.1, is different than my empirical probability, 0.16 repeating. Now you may say, well, of course, you only rolled it 10 times, so all you could get is accurate to the 10th place. But 0.2 would be closer than 0.1, so we've got a problem there. But that's what we do for experimental probability. We just try it. Do it again and again. I flip a coin, however many times, how many heads do I get? How many tails do I get? In fact, MIT did this. And they actually, yes, MIT did this, and they spent the time, the money, and the effort, and they flipped coins millions of times. And they actually found the probability of getting heads to be 0.51. I believe they used quarters for this experiment. So they found the probability of getting heads to be 0.51 and the probability of getting tails to be 0.49. So not the even 0.5 that we tend to claim. So if you're ever in a coin toss, call heads, you've got a slight edge over calling tails. So, but what did they do with that? Well, they took more times rolling. So let's say instead of rolling 10 times, I roll 100 times. And what I would do in a classroom setting is I would actually, after rolling 10 times myself, I would hand out dice to the members of the class and have them roll. And then we'd find out how many, and have them each roll 10 times and find out how. So if I have 10 people roll 10 times, and then I add them up, that's 10 times 10 or 100 rolls. So I find the probability of rolling a 3 is something over 100. I do that and I find out that they got 19 threes, which is 0.19, which is closer to 0.16 repeating than my 0.1. If I had them each roll 100 times, maybe I find out it's 0.173. Still closer again. So the law of large numbers says as an experiment is repeated over and over again, the empirical probability will approach the theoretical probability. So if I were to have them roll 1,000,000 times, then I would get that much closer to being matching the theoretical probability of 0.16 repeating. The law of large numbers. So thus far, this is, as I said, basic ideas of probability. We have the theoretical or classical probability, which is just number of desired outcomes over the total number of possible outcomes. We have the experimental or empirical probability, which is the number of occurrences over the number of trials. And then we have also the terminology and realizing that probability is always between 0 and 1, which means never tell me that the probability is 25%. That's the percentage chance. That's not probability. Probability is always between 0 and 1. 25% chance is not a probability. 0.25 is a probability. So if you come up with a percent for something and you want to turn it into a probability, just convert the percent into a decimal. 11.2% is 0.112 as a probability. Always between 0 and 1. You can never have a probability greater than 1. Probability of B cannot be equal to 1.2. That would be essentially saying that if I were to use that thing 100 times, 120 times, it would turn out to be B. Say what? Okay, if you had a probability greater than 1, it would mean that you'd have more occurrences of the desired outcome than you did trials. You rolled a die 100 times and got 120 threes. That doesn't even make sense. So avoid those errors, and probabilities obviously cannot be negative either. You can't have a negative probability. So what about sampling from a population? What if I have a frequency distribution of categorical data? Right, what if I have cars and I have the model, the make, so Toyota, Chevy, Ford, Mazda, and other. And so I go out into the parking lot and I determine how many there are of these. And I see that there are 27 Toyotas, there's 12 Chevys, 9 Fords, 7 Mazdas, and 31 other vehicles, other makes and models. So I've got all these, and I say, what is the probability that I go out there and of these vehicles, I randomly select a Chevy? Right? What's the probability that I randomly select a Chevy? Well, how many do we have in total? 27, 39, 48, 55, 85, 86. So I have 86 total, and there are 12 Chevys, so it's 12 over 86. Now, I don't care whether you leave a probability as a fraction or whether you convert it to a decimal. To me, that doesn't matter. But if you leave it as a fraction, and this may sound familiar from when I was talking about relative probability and relative frequencies way back when, right? If you leave it as a fraction, you have to reduce. Okay, so 1286 reduces to 6/43. So that would be valid. You leave it as 1286, I've got to take off a point. Okay, 6/43, or I can turn it into a decimal which gives me approximately 0.14. I get 0.139534883721. That's as far as my calculator gives me. But I round it. Make sure if you give it to me as a decimal that it is rounded correctly. Never round to a whole number. Obviously, you're dealing with probabilities. It's between 0 and 1. You round to a whole number, you're either saying that it's never going to happen or always going to happen. I do have that preference, and I've stated this before, I like to see 2 decimal places. Okay? The only time I say other than that is correlation coefficients, where I said I want to see 4 decimal places. So 2 decimal places is good. You give me more than that, that's fine. Don't give me all the digits in your calculator. That actually is showing laziness on your part. But make sure that if you give me a decimal that it's rounded correctly. Don't truncate. This was 0.13 something something something. I rounded it to 0.14. Don't truncate it to 1.3. Truncate means you chop it off instead of actually taking the effort to look at the next digit and see where you should round. So that's the probability of selecting a Chevy. What about the probability of selecting a Toyota or a Mazda? And I'm being lazy and just saying T for Toyota and M for Mazda. Okay, Toyota or Mazda, well that's 27 plus 7 is 34. So that's 34 over 86 or 17 over 43. And if you turn it into a decimal, gives you about 0.40. 0.40. I came up with 0.39534883729. And of course it keeps going from there. So be careful with that. Like I said, I like 2 decimal places. I saw the 0.395. That 5 would round my 9 up to a 10, making it 0.40. So I put that 0 in there because I did round to the hundredths place. So that's perfectly valid. But that's how we do it here. We sum it up, find out what our total frequency of our frequencies is, our sample size. And then it's just take the ones you want, put it over that sample size, and you get your probability. The probability of selecting a Toyota or a Mazda, 0.40. The probability of selecting a Chevy, 0.14. Okay? So just one more thing to discuss briefly. Now, sometimes we actually do experiments. MIT paid these people to flip these coins, these quarters, over and over and over again to verify the probability of getting heads. Well, that's great, but there are also times where we just don't want to do that. It's either too expensive or too time consuming, so we don't deal with that. In those cases, we do a simulation. Simulation is where we just use a computer program or something else to conduct a virtual experiment. We don't actually do it, we just have a program run that pretends to do it. Now, there are a number of ways that you can do that, doing these virtual experiments, and some of those ways that are done now, in fact, back a number of years ago, I used to teach statistics at another college, and they required a computer lab portion of the course. So we would get to probability, and I would have my students there flipping coins, and they'd have to flip 10 times, and we'd be looking at the law of large numbers and such. Flip it 10 times, then flip it 100 times, right? And then you go, it's like, boy, but we want to go higher. So what I would do is I would have them simulate flipping the coin 1,000 times or 1,000,000 times. So they would just have the computer randomly generate heads and tails and go through and do it. and that way they didn't have to flip the coin a million times. I'd have them roll a die 10 times, 100 times, and then I'd have them simulate 1,000 times or 1,000,000 times. And then I'd have them pull a card from a deck, shuffle a deck, pull a card from the deck, put the card back in, shuffle the deck, pull a card from the deck. And I'd have them do that 10 times. Now you can just imagine how tedious that would be just doing that 100 times. Can you imagine 1,000 times? So we would use the computer to simulate doing those larger number of times. So some software that is common for simulation of these things, one is Minitab. Minitab is it's like a spreadsheet, but it's specific statistical software for doing calculations. It works on columns or rows. You can't just select part of a column to look at, it looks at the whole thing. You'll either look at all of a column or all of a row. And Minitab was put out by Minitab Inc. To be honest with you, I've never seen it used outside of a college setting. I know that there must be places that use it, but I've never seen a place that uses Minitab outside of college. But it's very common for use in a college setting. Excel, Google Sheets, other spreadsheet software basically works with a whole bunch of cells, and you can tell it, you can put the values into it and have it do calculations for it and everything. So a very popular way, any sort of spreadsheet program. Obviously, Excel is by Microsoft. Google Sheets is obviously by Google, right? Goes through the whole thing. But any Office suite will have some sort of a spreadsheet program. And that's not limited to being specifically rows or specifically columns. You can actually select which cells you want it to look at. SPSS, Statistical Package for the Social Sciences. That's a very common one that you'll see. Many times you'll see that, especially if you are into the medical side of things, even more going into the psychology side of things. Statistical Package for the Social Sciences. It's actually by IBM. For those of you not familiar with IBM, big computer manufacturer, used to be one of the top ones. Lenovo got their ThinkPad from IBM. They bought IBM. So SPSS, Statistical Package for the Social Sciences. Another common one is SAS, Statistical Analysis Software, and that's by the SAS Institute. So that's another common one. These are ones that you'll see all over the place. Obviously, spreadsheets you see everywhere. Another one extremely powerful, becoming more into its own, is R. R is put together by the R Foundation. It's an open source software that can do pretty much anything you can dream of. Being open source, anybody can modify it, anybody can write programs for it. It's more of a programming language that you use to create any sort of a simulation. Works extremely well, extremely powerful, and the nice thing is, even though it's a programming language, you can find modules to add to it that will do pretty much anything you could want, because other people have already run into that problem and have written the modules for it. So very powerful. It's the type of thing that if I had the time in the class, I would teach people how to do R. Because it's free, open source, always being updated, has all these modules. You can do anything you want mathematically with R. So there we go. Basic ideas of probability.